Hello, AP Stats. Hope you guys are having a fantastic day. We are going to do Chapter 2. So this is the Practice of Statistics, 4th edition, 2.12 notes. So we're going to be talking about transforming data and about what a density curve is. So our SWABAT for today is describing the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape, center, and spread of a distribution of data, or the SOCs. Approximately, locate the median and the mean on a density curve. Okay. So first, just a couple of quick definitions. Linear transformations of data. So basically, right, what we're talking about here is if I have a set of data, what happens to the distribution of that data? So by distribution, I mean the histogram or the box plot, right, or the shape of the distribution of the values, the shape of the values. How does that change if you take every single data point and you multiply by a constant, or equivalently divide by a constant? And then what happens to that distribution if you add or subtract by a constant as well? So imagine you have a set of data. In this case, I'm going to pretend it's your scores, your test scores on your most recent AP exam. And not AP exam, your most recent test, right? So I've already entered the data. This is fake. This is not your real, these are not your real scores. But anyways, so I put all of the scores in list 1, L1. So you've got 60, 62, 64, 53, blah, 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 blah. Okay. You know how to enter data into your calculator, so you get there. So the question is, what happens if I multiply or divide every single value by a constant? So in this case, maybe I want to know what your actual percentage is. These are raw scores, and say the test is actually out of 75 points. So I actually want to know, A, what does this distribution look like? And then B, what does the distribution look like if I take those values and divide them all by 75 and multiply by 100, which would also get me your percentage score. So what I'm going to do, I'm going to go up to list 2, clear it out, don't delete it, clear it. If I go up to the top of list 2 and hit enter, I can actually take list 1 and multiply and divide by a constant for all the values, so I don't have to actually calculate it. So what I'm going to do is I'm going to say, okay, I want L2 to be my first list, L1, divided by 75, because remember the scores are actually out of 75, and then I want to multiply by 100 so that I get the raw percentages. Okay, so I hit enter, and then look at that. Now we've got an 80%, an 83%, an 85%, 70, 92. Okay, so those are your scores. So the question is, how does multiplying or dividing by a constant, which is what we just did, how does that affect the distribution of the data? So in order to do this, let's make two box plots side by side. So I'm going to go into stat plot, and I'm going to turn a plot on for, let's do a box plot. I could have done a histogram as well. And then I want to do L1. Okay, so those are my raw scores. And then I also want to do it for L2 to kind of compare them side by side. So let's turn plot 2 on, and I want to make another box plot with outliers. And I want to do it of list 2. Zoom stat, so zoom 9. Let's see what we got. All right, so does it look the same? I think not. So, because this is really weird. I'm actually in the middle of parent-teacher conferences, so at some point I might have somebody knock on the door. But anyways, so take a look, right? Your median, which is the middle number, right? On the blue, those are the raw scores. That has changed, right? It's over here. Also, the shape of the data, like the spread, has gone from here to it's spread out a little bit more. So what we want to look at is actually what happened to those values. So we want to look at what happened to the mean, what happened to the median, what happened to the spread, so the standard deviation. So we're kind of curious about that. So let's go back to figuring out what our mean and median and standard deviation are. So let's go to stat calc, 1 var stats, and I want to get that for list 1 first. Okay, so if I get it for list 1, I'm calculating all of my the numerical summary of the first list. So my mean is a 61.6. My standard deviation is 7.3 approximately, or 7.7, depending on if it's a sample or a population. And my median 63. Okay, so I'm going to go ahead and write those numbers down so we have them as a reference. Okay, so I've just written those down for. So I want to do the same thing for L2, right? Because L2 is our list of data that we've multiplied and divided by a constant, okay? So I'm going to go to stat, calc, same thing, 1 var stats, except I want L2 this time, not L1. Take a guess, what do you think is going to happen? Our mean is an 82.13. Our standard deviation is 9.747. Our median is an 84, and then our range is a 94.6 minus 66.6, okay? So we want to look at how those numbers compare. So I'm going to write those down so we can just kind of take a look at that. So taking a look at the difference between the numerical summaries between the two lists, you'll notice that like the mean that was 61.6 turned into an 82. And if you check it, 61.6 divided by 75, right, which is what our total score was, times 100, will be 82. So what you're seeing is that when you take data and multiply or divide by a constant, your mean will actually also be multiplied or divided by that constant as well. So next we have the standard deviation, and you could probably make a guess that the same thing's going to happen with standard deviation. So basically you're converting all of your data from points on the test to percentage. So in theory, your standard deviation, which is 7.31, if you divide that by 75 and multiply by 100, you should get your new one, 9.75, and you do. Okay, so anyways, same thing for the median and the range. So the only caveat is that if I multiply something by a negative number, the standard deviation is still the standard deviation doesn't become negative. So your means are multiplied by the constant, but your standard deviation is multiplied by the absolute value of the constant that you're multiplying all the data points by. Because remember, standard deviation is always positive. So yeah, cool. So putting that into our definitions, we've got that if you multiply or divide a set of data by a constant a, so this is just multiplication, but division will work the same way, your new mu, okay, will be equal to the old mu, but times a, okay. Your standard deviation, your new standard deviation would be your old standard deviation, but times the absolute value of a, okay. And then the median also is going to be your new median is your old median times a. Okay, so hopefully that makes sense. If you have questions, let me know. Now the next question is, what happens if you add or subtract by a constant? So this would be an example like, so I still have my data set from before, and instead of changing my values to percentages, perhaps I wanted to curve everybody's grade by 2 points. So I wanted to take L1 and I want to add 2 points to everybody's score. Okay. If I were to do that, then basically, right, your entire distribution, which was your box plot, just gets shifted left or right based on whether or not that's positive or negative. And so your mean also is just going to go up by 2 points. Your standard deviation, we should check. Maybe, again, go into our stat plot. So this is my new stat plot. Okay, and I want to zoom 9. So zoom 9. So my new data set is the red. And if you notice, it hasn't changed the standard deviation, or in this case, we're talking about range, but your spread hasn't changed at all. And that would make sense, right? Because you're not stretching anything. You're not multiplying numbers. You're just taking the distribution and then moving it left and right. You're not changing the spread, which is what multiplying does. So when you're adding and subtracting by a constant, you're the spread, standard deviation, range, IQR, any of the measures of the spread are not going to change, but the centers will increase or decrease by that constant, respectively. So if you're adding 3, the mean will increase by 3. If you're subtracting 3, then your mean will decrease by 3, median as well. So next is a density curve, and I'm basically going to just show you what a density curve is and give you a couple things that you need in order for a curve to be a density curve. So say, for example, you have a histogram, okay, like the one shown. So if you notice, right, if I wanted to know, say these are number of siblings, number of pets or something. If I wanted to know what number of people in the study liked pets, have 4 pets or less, then I would add up this column and this column and this column and this column on the histogram to try to figure it out. So the thing is, when you get to really, really large data sets, if you make a smooth curve, so the one that's shown here, right, a smooth curve that like generally fits the data, then the area under that curve that's below 4, so here's your 4 mark, so the area underneath that curve, so that would be like this region here, is going to be really, really close to the true value had you added up the bars. And it's actually a lot easier to calculate. So so basically, long story short, a density curve is a curve that shows you the general trend of a histogram or of a graph of a distribution of data. So, long story short, a density curve is a curve that shows the general trend of a set of data, and it must be above the x-axis. You can't have like a negative density curve, and the area underneath it has to equal 1, and that the area under the curve is actually equal to the proportion of values that are under the curve. So basically what that means is if I have a density curve like this, and I want to know what percent of people have scores between 80 and 90, I can find the area under the curve, and the area is equal to the percent of people who have scores between 80 and 90. So that's what that means. So the next example is basically kind of the same thing I did that I showed you before with the graphing calculator, but a different set of data. So you've got a group of students in Australia guessing the width of their classroom to the nearest meter, so that, they have 8, here's your data set, and then they include the stats and the distribution for that. Go ahead and answer the next couple of questions, and hopefully it's nice now. Oh, look, I'm drawing. So here are your solutions. Describe the distribution above. It is quite skewed to the right. So remember, for describing a distribution, you need your socks. So shape, outlier, center, and spread. So because it is skewed right and has several outliers, which I've shown how to calculate the outliers there just in case you forgot. It's like Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR, and then anything outside of those ranges will be outliers. So there are 3 high outliers and no low outliers. Because the data is skewed and we have outliers, probably the best measure of center is the median, which is 15, which you get from here, right? The median's 15, and then you're using the IQR or the range to measure spread, not standard deviation, because of the skewness and the outliers. So measures. Okay, so again, this is just kind of like a repeat of what we did before. pause it if you need to read that. But anyways, we want to talk a little bit about z-score. So how does this relate to z-score? So remember that your z-score is your x value minus your mean over standard deviation. And so basically you're taking, for each individual value, you're taking that value, subtracting the mean, so you're taking it and you're shifting it over whatever the amount of the mean is, and then you're dividing by sigma, so you're dividing by a constant, which changes the spread. So anyways, if you went through your calculator and you did this, hopefully you can kind of skip through how to do it in your calculator. But I want to put in list 2, I want to put all the z-scores. So I need to take the value from list 1, and I'm actually going to use parentheses here so I don't mess anything up. So I'm going to do the value from list 1, so it would be 8 minus the mean, and in this case, the mean was, oh, do we remember? I don't think we actually, oh, the mean, it's right here. So the mean is a 16.02. So in our calculator, note that you don't actually have to calculate it. So in our calculator, we take our value from list 1, we subtract the mean, which is 16.02, and then we divide by the standard deviation, which is 7.14, and hit enter, and then it should fill the entire list 2 with all of your z-scores. So 8 is negative 1.123 standard deviations below the mean. So anyways, you do that, and then to answer the questions here, what is z-score? So if you take a look and you plot your 2 plots, plot 1, which is all the regular, your raw scores, and then plot 2, which is all your z-scores, zoom 9, you can, so the scale is kind of funky, but these are the original data points, and then here are your z-scores. Okay, notice that it is centered around 0, and it's been squished. And so what you'll find is that using the transformations, your new mean is your original mean minus 16.02, which is the standard deviation. And so that should be 0. Okay. And then your new standard deviation is your old standard deviation divided by your standard deviation. So, well, actually, okay, so that's 1. So if you are graphing the z-scores, you should end up with a distribution that is centered around 0 and has standard deviation 1. So if you have questions on that, let me know. Last but not least, I want to go just kind of briefly touch on the median versus the mean on a density curve. It's the same thing as when we were talking about histograms, but your mean or is your balancing point. So if you had to put your finger underneath to balance, where would it be? And so kind of like, okay, here's my distribution, and like, oh, you need to kind of adjust where your mean is to balance it out based on the skewness. So in a perfectly symmetric distribution, your median and your mean are going to be in the center. And in a skewed distribution, same thing as before, your mean's going to get pulled a little bit towards the outliers. And your median is going to be towards the other, here's your median, and then your mean gets pulled towards the outliers. The median is the halfway point, which means that you have 50% of the data above the median and 50% below the median. Okay, so both of those areas should be 50% or 0.5. And same thing with these other 2 distributions. Okay, so that's our long story short, and hope you got it. Yeah, I'll see you in class. All right, have a great day. Bye-bye.